Hi class, welcome to Unit 3, Lesson 7, where we look at magnetic force on moving charges. So today's learning goal is you'll be able to demonstrate an understanding of magnetic force on moving charges, motion of charge in magnetic field. You'll be able to analyze the working of magnetohydrodynamic propulsion and cathode ray tube. The success criteria. I know I've achieved these goals if I can describe in detail magnetic force on moving charges and its direction, motion of charge in magnetic fields, investigate the working of magnetohydrodynamic, or MHD, propulsion and cathode ray tube to find charge to mass ratios, to solve problems related to magnetic force on moving charges, and applying learning to daily life problems and thinking. If you place a compass needle next to a conductor, then connect the conductor to a DC power supply, the compass needle turns, demonstrating that the current in the conductor produces a magnetic field, which interacts with the magnetic field of the compass needle. Therefore, a current can exert a force on a magnet. Hence, two conductors with currents can experience a force between each other. Place two conductors, wires, side by side, both with a current passing through them, and they will attract or repel each other, hence exerting a force between each other. And this means that a magnetic field can exert a force on a current or moving charges. If a current produces a force on a magnet, then the magnet must produce an equal but opposite force on the current. So the magnitude of this magnetic force on the charged particle, i.e. the magnetic force from the magnetic field onto the current or moving charge, is represented by the vector Fm, and it's directly proportional to the magnitude of the magnetic field B, the velocity v, and the charge q on the particle. It's also proportional or depends on the angle between the magnetic field of B and velocity Vw. So the theta between those two. When theta is 90 degrees, the particle is moving perpendicular to the field lines. The force is at a maximum. And when theta equals 0 or 180 degrees, when the particle is moving parallel to the field lines, the force vanishes. Because as we'll see, sine theta is 0. This is consistent with the fact that the magnitude of the magnetic force experienced by the charged particle is also proportional to sine theta. So combining these, we come up with a formula. The magnetic force is equal to Q times V times B times sine theta. And so here are the SI units for each of them. Mostly as you expect, but one to point out is the magnitude of the magnetic field strength is in Tesla, which is represented by capital T. And keep in mind, if you're ever converting, that 1 Tesla is equal to a kilogram per coulomb times seconds. So we've come up with a way to get the magnetic force magnitude, but what about its direction? Consider a plane parallel to both the magnetic field B and a velocity v of a charged particle. The force is perpendicular to this plane. So picture this plane here as this 2D plane, where it's parallel to both B and I, or this is V. V is also in the same direction as I. So if this is the case, then it's perpendicular to this plane, meaning it's 90 degrees either up or down. But which direction is it? Well, a simple right-hand rule can be used to determine the direction of the force. If the right thumb points in the direction of motion for a positive charge, and the extended fingers point in the direction of the magnetic field B, the force is in the direction in which the right palm would push. So that's this example here. Our right hand our fingers are pointing to the direction of the magnetic field, B, and the right thumb points in the direction of the motion of a positive charge, which is going this way. Then pushing upward, you can see how the palm would follow this arrow. It would go perpendicular to the palm and up. But if the charge is negative, just reverse the direction of your thumb when using the rule. So for this case, you would set up your way like this. You'd say your velocity is going that direction labeled here, right? This direction, so you can see magnetic field line of B is going this way. So you line up your hand like this, but then you ask yourself if the charge is negative, then you simply flip your hand, you reverse the direction of your thumb, so it's, you get the idea this way. Except your nails would be on the top at that point because you're flipping it, right? There. So in other words, you point your thumb in the opposite direction of the velocity of the charge. This works because a negative charge flowing in one direction is equivalent to a positive charge flowing in the opposite direction. So either way, in either way that you like to do it, if you set it up first and then flip it, then that's fine. Or if you think of it in this way, but usually it's best to just set it up like a positive charge and then ask yourself if the charge is positive or negative and flip accordingly. So in this case, it'd be pointing down, palm direction. So let's look at a problem. This magnet is similar to a parallel plate capacitor in that there is a strong uniform field between its poles with some fringing on the sides. Suppose the magnetic field strength inside is 0.07 Tesla and a 4.3 millicoulomb charge is moving through the field at a right angle to the field lines. How strong and which way is the magnetic force on the charge? So we're looking for Fm in magnitude and direction. We're given a B here. We have Q. And in this diagram, we're also told and given that our V is 5 meters per second. And so we have our equation from equation before. We have our Q, V, B, and our sine theta. We're told that the charge is moving through the field at a right angle to the field lines. And so we have our theta as well. And so in our FQVB sine theta, we have QVB and our sine of 90, which turns out to be 1. So we just have F equals QVB. And we have all those values. And we plug them in and get F equals 0.0015 newtons. And it asks us for the direction as well. And so we have to identify if the charge is positive or negative. Clearly we can tell by the positive value that it's a positive charge, otherwise it'd be negative. So we can, it's a positive value. And so that means that our right hand rule is going to involve no flipping. So it's just going to be for a positive charge. And so if we use our right hand and line up if we put our fingers in the direction of these field lines, and then if we put our thumb in the direction of this direction, we get a hand like this. And then, like I said, there is no flipping because we take a look at the charge, it's positive, and so we can tell that our palm would be up, like coming at us. So, and hence we say directed out of the page. So it's coming out, directing out of the page. So let's talk about magneto-hydrodynamic propulsion, known as MHD. The Yamamoto 1 is the first ship to apply this principle, the same principle from last time, in propulsion. Instead of using propellers, it uses MHD propulsion. It exerts a magnetic force on a current. A typical MHD propulsion unit uses a large superconducting magnet to create a strong magnetic field. Large metal parallel plates connected to either side of the unit have a large potential difference across them caused by a DC electric generator. This creates an electric current in the seawater due to the presence of ions perpendicular to the magnetic field. If you'll notice in this diagram, the right-hand rule applies, and it sends our force this way. And as this force is applied to the seawater, it pushes back and sends the ship this way, where the electromagnetic force is applied to the seawater this direction. And so, as we said, the right-hand rule applies for this, and so when it expels this water in this direction, it's pushing this seawater out, expelling in the direction of the force from our right-hand rule. According to Newton's third law, if the unit pushes the water out the back of the ship, the water will exert an equal and opposite force on the ship, causing it to move this direction. So on its FBD, this force would show up, this one would not. But this is not an FBD. So it's a very clever way of thinking and manipulating using this magnetic force of a plate system. So back to charge motion in magnetic fields. Consider the trajectory of a charged particle in a magnetic field. Since the magnetic force is always perpendicular to V, it changes the direction of V, but has no effect on the magnitude of the velocity or speed. This is true because no component of the force acts in the direction of motion of the charged particle. And so this kind of looks like something we've seen before. If you recall centripetal acceleration and particle moving around like that, we noticed how the acceleration wasn't changing in magnitude, it was only changing in direction for uniform circular motion. And so we kind of see that here. If the magnetic force is the sole force acting on the particle is equal to the net force on the particle and is always perpendicular to its velocity. This is the condition for uniform circular motion. So just like we mentioned, that's exactly what it models. In fact, if the field is strong enough and the particle doesn't lose any energy, it will move in a complete circle as shown. Ideally, a charged particle will move in a circle because the magnetic force is perpendicular to the velocity at all times. And so we get exactly what we were looking at before with our uniform circular motion, except we now have a magnetic force is the one pointing to the center. We have our familiar velocity or speed velocity vector, and we just have a magnetic field going on now. And notice how it's perpendicular to the V. So we represent these magnetic fields in two-dimensional diagrams by drawing X's for field lines directed into and perpendicular to that page, and dots for field lines pointing out of and perpendicular to the page. So an easy way to remember this is use an arrow from a bow and arrow. So if you were to view an arrow coming at you, you would see that the point, the dot coming at you, and if you see it going away, you would see the back feather part. So that's an easy way to remember the field lines for these. And so if the velocity is perpendicular to the magnetic field lines, then both the velocity and the magnetic force are parallel to the page. Hence you see the v vectors and the force vectors are parallel to the page, this page plane. And notice how b in and out are perpendicular. So if you notice, our right hand rule still applies for this diagram. So if we took this v and a b of in, because our arrows are going, the x is in, remember, away. So if we pointed our fingers into the page, and then we chose this velocity vector, so that means our palm will be facing up because our fingers are going into the page, and our thumb is going to the direction of the velocity vector. We then ask ourselves, are we dealing with positive charge or negative charge? We're dealing with negative charge. That means we just do our flipped, like we do for our right hand rule. And so we go from our palm that looks like this, going into the page. We have to flip it to this. And nails up, our palm is facing down. Our fingers are into the page. This is parallel to the page, this is our V. And when we see that, our palm is pointing down. Rightfully so, because it matches this. So our right hand rule still works for this. So try it yourself, because it's a little hard to draw out, but you'll understand if you point everything in the right direction. Ask yourself the charge, it will still match. So this idea has another application. So a positively charged particle of mass m and charge q is shot to the right with speed v. By the right hand rule, the magnetic force on it is up. Since v is perpendicular to b, Fm simply equals qvb. Because Fm is perpendicular to v, it has no tangential component, and so it is entirely centripetal. Thus, F causes a centripetal acceleration, just like we saw with our uniform circular motion. As the particle turns, so do V and F and B. And if B is uniform, the particle moves in a circle. This is the basic idea behind a particle accelerator. Since F is the centripetal force, Fc equals mv squared over r, let's see how speed, mass, charge, field strength, and radius of a curvature are related. So because of this, F is the centripetal force, we're allowed to make this Fm equals Fc. Plug in our centripetal force formula we're very used to, mv squared over r. Our magnetic force formula without the sign, because, well, it's still there, it's just equal to 1 because they're perpendicular. And if we solve for r, we get mv over qb, which is something that's not easily measurable, but you can find this radius using this method. So let's look at a problem. An electron accelerates from rest in a horizontally directed electric field through a potential difference of 46 volts with delta V. The electron then leaves the electric field, entering a magnetic field of magnitude 0.20 Tesla. B directed into the page. So part 1, calculate the initial speed of the electron upon entering the magnetic field. So this is going to be our V. But so just to not be confused, these are the same picture, same scenario, but just zoomed in. And for one particular spot on the wheel, and that looks like it's this top V because the V is going to the right. So this is just a snapshot of one of the spots around the circle. So if you can recall from our last lesson, we had said when we were looking at charges moving through an electric field, particularly charges in motion, we had said that the electric potential energy, as it moves from it was from that R1 to R2, any electric potential energy it loses, it's converted into kinetic energy as it increases, covers more and more distance. Or as it moves more kinetically, I should say. So that means that we can say the change in electric potential energy is equal to the change in kinetic energy, because the electric potential energy lost by the electron is gained in kinetic energy as it moves. And so when we have this equation, we know from a few more lessons ago that we had said that electric potential energy is equal to Q times the potential difference, delta V. And so we sub that in. Kinetic energy is half mv squared, and so we want to isolate V. We also square root, so we isolate V squared, square root it, and we are given our potential energy, potential difference, 46 volts, and we know the magnitude of the charge of an electron is 1.6 times 10 to the negative 19 coulombs. Magnitude, of course, we would use a negative sign, but we're not interested in that. We're interested in the speed, so we just need the magnitude. Also, that would cause problems with our square root here. So we have our Q, and our mass is given by an appendix. This would be given if you were needed it would be given to you. So from our appendix, it is 9.11 times 10 to the negative 31 kilograms. So we plug all that in, we get our V of 4 times 10 to the 6 meters per second. And so the initial speed of the electron upon entering the magnetic field is 4.0 is our value. So part 2 is calculating the magnitude and direction of the magnetic force. So that's our FM. And so we were very comfortable with finding that. We use our magnetic force formula that we've been looking at in the past few slides. We have our magnitude of our charge. We just found the V. We're given our B, and the angle we can see from our drawn out diagram is 90 degrees. Going into the page and this V here, for any V really, are all perpendicular to the magnetic field of B going in. So we know that's 90. And so we plug in our magnitude for our Q, and we just found our V, our B that we're given, and sine 90 degrees because they're perpendicular, and we get the magnitude of the force, 1.3 times 10 to the negative 13 newtons. But now we need to find our direction. How do we find that? We use our right-hand rule. And so we go to our drawn figure, and you pick one of the corresponding points, but we're going to pick the top one, which looks like this. And so if we put our fingers into the page and put our thumb in the direction of this velocity at this moment, right? It has to be this velocity. Then we see our palm faces up, but we do have to remember that we're dealing with an electron. So we ask ourselves, oh, is this a positive or negative charge? It's negative, so we do our little flip, and our thumb goes the other direction, making our palm face down, and that makes our palm, our F force, point in this proper direction for this particular V. And so we do say that our palm now pushes down toward the bottom of the page, and therefore the magnetic force is Fm 1.3 times 10 to the negative 13 newtons down. The last part is calculating the radius of the electron's circular path. And so in the last slide, we just had seen this in our particle accelerator. We had said that in this situation, Fm equals Fc, and we can come to derive our formula right here. And we said that radius is not easily measurable, especially for a charge. So this formula is very useful for measuring that radius, so it would be hard to measure. And so we have our formula here. We are given our mass. We had found that V in part A. We are given our B, and we have our Q. So we simply plug in everything with their appropriate units, and we come up with our radius that we otherwise wouldn't be able to come up with, which is 1.1 times 10 to the negative 4 meters. And so our final statement is with that value. So when we were talking about Millikan and his oil drop experiment, we had mentioned that just before him, Thomson had found out the charge to mass ratio for particles, and that Millikan found out exactly the elementary charge amount. But the charge to mass ratios were what Thomson was worrying about, and he had used an apparatus in the next slide to accelerate a thin beam of electrons between the parallel plates and the coils. And so this beam of electrons, applying either an electric field or a magnetic field across this tube, caused the beam to be deflected up, down, left, or right relative to its original path, depending on the direction of the applied field. Thomson concluded that the cathode rays consist of negatively charged particles moving at high speed from cathode to anode. He called these particles electrons. When there is a current in the coils, it creates a magnetic field of magnitude B, which deflects the electrons along a circular arc of radius r so that they hit the end of the tube at a point x. And so similarly, we come to a similar result of that formula before, where we can measure our r here. Similar to here. So here's the figure of his cathode ray tube. The path of the electron is curved only in the magnetic field of the coils along a circular arc, or the electric field of the plates along a parabola. After leaving these fields, the electrons move in a straight line to points x or y. And so we see in this example we have electric field plates. Here we have more plates rather than the and so notice that the path of the electrons here curve in a type of parabola here, because it's in the electric field of the plates. And when it leaves this region, here is when it starts going back into a straight line. And this is what we mean by going to point x or point y. It continues in a straight line here. but notice how it curves in a parabolic or sometimes a circular arc in this magnetic field area. So to determine the electron speed v, Thomson used a set of parallel plates. When a potential difference is applied to the plates, with the lower plate being negative, and there is no current in the coils, an electron is deflected upward, reaching the end of the tube at point Y. With current in the coils and a magnetic field again acting on the electrons, the potential difference across the plates can be adjusted until the two deflections, electric and magnetic, cancel, causing the electron beam to reach the end of the tube at point Z. When this has been done, we can come to this derivation. From Fm equals Fe. And so Thomson could now express the ratio of charge to mass for electrons in terms of the measurable quantities of electric field strength, magnetic field strength, and radius of curvature. So by this, if this is equation 2, and our one from before was 1, put our second one into 1, we come to this expression, which has both the charge and mass in it. And when you solve it into the ratio form of E over M, charge to mass, having a ratio of that, we get the other value in terms of electric field strength, magnetic field strength, and R. And so he had a measurement for the charge to mass ratio equaling this expression. And so what he found it to be, to 3 significant digits, is 1.76 times 10 to the 11 coulombs per kilogram. And this was the charge to mass ratio he sought out to find. And so as we mentioned, this happened before, but then a few years later, Millikan had determined the charge on an electron to actually be the elementary charge, which is a step further. Combining these two results, we find the electron mass to be 9.11 times 10 to the negative 31 kilograms. So thanks to each one of their pieces, they could come to the electron's mass, and each of their pieces alone we have a ratio and actual elementary charge value. So we have both of these values thanks to their work. So in our examples, we saw mostly electrons moving perpendicular to the magnetic field lines, but what if we say that they're moving when they're not moving perpendicular to the magnetic field lines? Well, that means the component of the velocity parallel to the lines is unaffected, and the component perpendicular to the field lines rotates. Together, these two components combine to produce the spiraling motion of a particle. So this diagram is a representation of that. We see the V is no longer parallel to B here. And notice what it does. It makes this spiraling motion, whereas before it was perpendicular. So it starts off in the same direction as B, parallel here. And when it's not moving perpendicular to the magnetic field lines, like in this case, it becomes no longer parallel to B because of the spiraling motion here. Notice how it's slanted now. It's been affected. Its vector is not like it was before. So notice this, at this point, this V is no longer parallel like it once was. And in another case, if the magnetic field is not uniform but increases in magnitude in the direction of motion, the force on the electron due to the magnetic field will slow the charges by reducing the component of the velocity parallel to the field, and may even cause the spiraling electron to reverse direction. So when you take some of these assumptions away, some crazy things start to happen. So that's everything for today.